Hello everyone, and welcome to another lecture of School of Solana organized by Eki. And today we will be talking about fuzz testing, and in particular fuzz testing of anchor-based Solana programs using our tool called Trident. So what will you learn today? At the beginning, I will tell you something about fuzz testing, what it is, and what are the pros and cons. And then we will speak about Trident, why we have developed it, and what you can do with it. And we will also go a little bit more deeper and talk about Solana fuzzing specifics, about the Trident fastest life cycle, how you can actually develop fastest, and what will be the workflow. And at the end, of course, I will show you a hands-on example where we will develop fuzz test for a simple anchor-based program using Trident. So what is fuzz testing? It is also known as fuzzing, and it is an automated software testing method. So it is not fully automated, and the developer has to develop at least part of the fuzz test. But finally, the fuzzer automatically generates and runs, let's say, thousands or even tens or hundreds of thousands of test cases for you. And it does it in a way that it passes malformed or invalid or some unexpected inputs to your program. And it basically tries to crash your program. Why you should do that? It is another testing layer that increases the robustness of your program, and it gives you another level of confidence that your program works correctly. By fuzzing, you cannot exclude existence of bugs, but as I said, it gives another layer or level of confidence. And yeah, so as I said, the fuzzer tries to crash your program. So it basically checks for runtime crashes that are not handled, or it also checks for crashes that are caused by so-called invariance violations, where a developer can define different invariants, and if these invariants are violated, then a crash is detected. What are the benefits of fuzzing? So it's often said that it will most likely find bugs that are missed by other tests. So it is due to the nature of fuzzing, which is automated, and it is kind of random. It really generates unexpected data for the program that are sometimes not intuitive, and that are or can be missed by usual, let's say, unit tests or integration tests that are done by humans or the developers. And it increases test coverage. This is kind of obvious. And the next point is that fast tests are usually easy to scale. Often it is possible to test on multiple machines, for example, be the same fastest or having different fastest targets. And also another or the last benefit here mentioned is so-called set it and forget it. So if you have your fastest written in a robust way, there is a good chance that in case the API of your program does not change, that you can just reuse a fastest, even though you have done some changes to your program, as soon as your invariance checks are general enough. Yeah, but everything is for a certain price, so there are some challenges. And the first of them is complicated environment setup. So it's fuzz testing, it's not an easy topic, and it might be quite challenging to set everything up, especially also if you have different dependencies of your program. And in the same way, also setting up the testing harness might be quite complex and time consuming, especially if you develop a new project and you would like to develop fuzzing testing harness from scratch, then it might take some time. And the last point here is data analysis crashes. So as the tests run automatically, there might be really a lot of data generated and a lot of crashes generated by the fuzzer. So you must expect some challenging during the analysis, especially if there are maybe some false positives, crashes. So yeah, you should basically analyze quite a lot of data here. And all these challenges were actually the reason why we decided to develop Trident, our fuzz testing framework. And it was in order to lower the fuzz testing entry barrier for new developers and basically to make the fuzz testing faster and easier. Yeah, and the tool is written in Rust, obviously. We're on Solana, and it supports Solana Anchor programs. Anchor programs because Anchor actually is well structured and it sets well-defined API of the programs, so it is quite convenient to build another tooling on top of it. And Trident automatically sets up the testing environment for you. It generates also the fuzzing test harness for you, so you don't have to do it manually. And it also provides a convenient CLI tool to run and debug the fuzz tests. And the fuzzing library is actually based on Google's HonkFuzz. So yeah, we didn't want to reinvent the wheel. HonkFuzz is a well-known fuzzing library used also for other or in other languages, and there is also a Rust crate. So this is what is used by Trident under the hood. And Trident is, of course, open source. It has been developed also with the help of the grant of Solana Foundation. So yeah, you can check the project on GitHub, Eki blockchain, Trident. So yeah, feel free to submit any feedback or issues or pull request on GitHub. So how can you fuzz test a Solana anchor-based program? I hope that all of you are familiar with the Solana programming model. If not, then I highly recommend you to pause this video now and read something about instruction data and instruction accounts. Because these two are actually the first two candidates that one would like to fuzz test. The instruction data are data passed to an instruction that are specific to each program, and based on this data, a particular program executes different actions. So the data has to be parsed, and then the program, executes a particular action, and that's why it is reasonable to generate random data or pseudo-random data in order to test for different edge cases. And this is the same situation also for the instruction accounts. So as you know, the Solana programs are stateless, so it means they do not contain or save any states, and all the states are saved into accounts. So programs first read data from accounts and finally write to the accounts back to store data. And therefore accounts are another source of vulnerabilities that that you have to check, and that's why if you are fuzzing your program, you would like also to generate, let's say, different accounts with some pseudo-random data in order to test your program. And the third point here is the instructions invocation order. So another vulnerability is that an attacker may execute instructions in an unexpected order, which may, for example, give access to some funds that should not be accessible, and so on. So this is another thing that should be tested, and very often the integration test let's say happy path scenario and test the actual functionality, but to test different path and unexpected invocation orders is much harder. So that's why this is something that can be done using fuzz testing. And finally, combinations of all of the cases above are of course possible, and sometimes if only a combination of these three situations will give you some vulnerability. So now let's look into Trident in order to understand the life cycle of a fuzz test. And for that, I have prepared here, and I pasted a diagram and an extract from a Trident documentation. Actually, Trident is running in a loop here on a diagram. And there are different ways how you can end this loop. So it runs within the loop until an end condition is met. And the first condition that can end the loop is that the maximum number of iterations is reached if the max number is specified. So of course you could leave your fuzzer run indefinitely. And then there is another condition that your fuzz test may be ended or may finish if a crash was detected. Again, if you decide to set the exit up and crash parameter. And if none of these conditions are met, then of course a user can interrupt the test manually, for example, by hitting Control C or by invoking any other interrupt signal. And so basically in each iteration of the fuzzer generates a sequence of instructions to execute. And now let's zoom into the diagram on the right to go a little bit more into detail. So we will focus first on the upper part of the diagram. And here, as you can see, the fuzzer starts with the first iteration 0. It compares if the maximal number has been reached, if it has been set, and if not, then it continues to the generate instructions block. Within the generate instructions block, there are some optional methods that developer can use in order to modify the way how the instructions are generated. So there are three types of instructions: the pre-instructions, instructions, and post-instructions. And what it allows us to do is to customize the instruction sequence. So using the pre-instructions method, developer can specify which instructions should be invoked at the beginning. So this might be useful, for example, I guess most or a lot of Solana and Anchor programs do, that there is some initialization instruction, and actually it doesn't really make sense to run the other instructions before the program is initialized. So it might make sense if you want to try something, or if you want to yeah, try, for example, some reinitialization or something like that. But anyway, here the pre-instructions method gives you the possibility to call the initialization method and then yeah, run other instructions or generate the other instructions randomly. And in the same way, you can use the post instructions in order to invoke some instructions at the end of the generated sequence. So yeah, at the beginning, the instruction sequence is generated. And once we have that, we can go to the lower part of the diagram where there is again a loop where we iterate through the instructions that were generated in the previous step. And we are iterating in the order that we specified previously. And the first thing that is called is the get accounts method. And this is a mandatory method that has to be specified by the developer. And yeah, in theory, it would be possible to all the time generate random accounts here, but in practice, it is not feasible because the fastest would be simply stuck in most cases, as the programs usually expect some kind of account that has either defined a structure or has a particular owner or has a specific address or something like that. So we have to specify the accounts here that should be submitted to the transaction in order to reduce the space complexity of the fastest. And then the next method that is called is the get data method. That is also mandatory and has to be specified by the developer. In this case, it would be possible to only submit random generated data as far as these data can be correctly deserialized to the expected data types. However, again, very often it makes sense to somehow restrict these data, especially if we know that, for example, there is some particular data range expected and checked in the program. So it would be possible to let the fuzzer figure out what kind of or what is the correct range of data, but very often it makes sense to reduce the complexity of the fastest by specifying or by narrowing down the range of the data. All right, and once we have that, then Trident actually takes so-called snapshot of the accounts that will be submitted to a given instruction. And it does it because, yeah, it has to save the data that are inside the accounts before the instructions. Then the particular instruction is invoked and executed. And here actually we have three scenarios. So the first scenario that we will talk about is that the instruction is executed correctly and it returns the OK result variant. In that case, we are expecting that some of the accounts were updated because the program has to write back to some of the to the mutable accounts, let's say. And yeah, once we have these two snapshots of the accounts before and after the instruction execution, then the last block here is executed. This is the check method, which is optional and where the developer can specify different invariant checks that are based on the data that are in the account before and after the instructions. And yeah, also based on the instruction data. And now either the checks pass and we are going back and we are continuing the iteration or the loop over the instructions, Or there is another situation where a check does not pass. In that case, the fuzzer detects a crash, and if a crash is detected, then all the input data that were generated by the fuzzer are saved to a crash file that can be used later on to reproduce this crash and debug the problem. So this was the first scenario where the instruction was executed correctly. The second scenario is when the instruction returns an error variant of the result type. And this is a situation when there is some, let's say, handled and expected error that the developer was thinking about. In that case, we don't have to continue this workflow or this program flow, because all the account states that were submitted to the instructions are reverted to the original state and nothing is updated. So it does not make sense to do other checks here. The developer can either decide that it will continue the iterations over the generated instructions, or it will just skip everything and go to another fuzzer iteration. So this was the second scenario. And the third scenario is when the instruction crashes. And this might happen if there is some, let's say, unhandled runtime error. And an unhandled runtime error, it might be, for example, if you try to unwrap an error result, or if you try to unwrap option that is none, or other runtime errors, as for example, index out of range, or something like that. So in that case, the program crashes, and the fuzzer detects the crash and again saves all the inputs that were generated by the fuzzer to a crash file, so that you can debug this crash later on. And the last slide that I would like to share with you before we will go to the hands-on example is the let's say basic fuzzing workflow. So yeah, developing a fuzz test is kind of an iterative process. So at the beginning, you probably will have to start with some analysis of the system under test. So at the beginning, it's ideal if it is a person that is not familiar with the implementation of the program, as it is often a good practice to separate the tester and the developer. So at the beginning, you should, however, have at least some high-level understanding of the program that you are testing. And based on that, you should determine the input. So as I was telling you before, it's not reasonable to let the fuzzer completely unbounded, because the space complexity of the test would be most probably too high and your fuzzer might be stuck. So that's why you have to determine the inputs, determine the correct accounts that should be submitted, but at the end try not to not to narrow so that you are sure that still different combinations of accounts, for example, are still tested. So yeah, first you should, or the second step is that you should determine the inputs. Then you should write and create your fuzz test and basically run your fuzz test. And then most probably your fuzz test will crash and you will have to debug the results. And there are different possibilities. So either you will find out that you have some problems in your program that you have to correct, or you will have to debug your test. You will maybe find out that some of the instructions are never executed because maybe some condition is not met that is checked in your program. So then you will have to start again with the analysis of the system under test, determine the correct inputs, and so on and so forth. All right, so this was the introduction, and now let's go to a hands-on example. For the hands-on project, I prepared a simple anchor program that we are going to pass. So if you want to follow along, you can just clone this repo from our GitHub, Aki blockchain, and then it is sos-trident. So I have my code already locally, so I will not clone it. And before we begin, we will also install all the necessary tools and dependencies that we will need. And for that, I recommend you that you can go to our documentation. So you can go to our page here, aki.xyz/trident/docs. And there in the installation section, you will find everything that you will need. So I expect that you have everything related to Solana development already installed, which would be Rust, Solana Tool Suite, and also Anchor. If not, then just go ahead and install it. And we will also need to install the Fuzz crate and the library using Cargo, and finally Trident. Yeah, in order to install Fuzz, you can click here the link to get detailed description. But otherwise, it's very easy. You can just type cargo install Fuzz. Like so. So I have it already installed, so that's why it was quick. And then we can directly install also Trident, which will be cargo install Trident-CLI, like so. And also in my case, I have it already installed. So in your case, I expect the packages will have to be compiled first. So feel free to pause the video now and do the installation. Now we have everything prepared. So let's just try to compile the project to make sure that everything works. And yeah, so I have compiled it before, but for you probably it will take some time. And in the meantime, we can also check quickly the source code. So the project, it is a classic Anchor project with the usual structure. We have here the programs folder with a program that is called unauthorized access to. It is actually one of the examples that comes with Trident. So later on, you can also check it there. And if we check the code, it's a very simple program. There are only two instructions, initialize and withdraw, that are implemented in separate files, initialize and withdraw. And yeah, we don't have to go too deeply right now into the source code because yeah, at the beginning we will try to write the fastest without really knowing some the implementation details of our program. Now, if your Anchor program was built successfully, then we can initialize Trident, and this is very easy. You can just type Trident init. But maybe before we will do that, I recommend you also to check the help. So you can just type Trident help in order to see all the commands that are available to you. And also you can, for example, type Trident help init, and it will give you further details what you can do with this command. And Trident has here one argument that can specify the type of test that you would like to generate. And the default behavior is that it generates the templates for fastest and also the integration tests or proof of concept tests. In this video, we are going to write only the fastest, so we can initialize only the fastest. So let's type Trident init Fuzz. And now Trident actually first has to compile your program. It was not compiled beforehand, and now it's expanding your the code and parsing it in order to generate the test templates, and it will take some time. So I will go back when it's done. Okay, and now the Trident initialization is finished. And as you can see, there are some new files that were generated for us. And there are also some configuration options that were modified. So let's quickly check the code editor. The whole idea of Trident is that the developer won't be obliged to modify the program source code. There is actually a new and self-standing project. And everything is generated now in the Trident tests folder, where there is also the fastest folder, and each fastest is then in a separate folder. Now we have one fastest fuzz_0. And therefore also the cargo toml file has been adapted, and the Trident test folder has been added into the workspace members. And finally, there is a new configuration trident.toml file that contains different options that you can configure. We will go back to the file later on. So now if we will go to the fastest folder and the first fastest 0, you can see that there are 3 new generated files. The first file that we will look at is the test_fuzz.rs file, and this is the fuzz target file with the main function. This is the file that is executed, and as you can see, it contains an infinite loop and a fuzz Trident macro. And this macro actually automatically adds a boilerplate for you that basically transforms the random data that is generated by the fuzzer, which is an array of bytes. And it transforms this data into an array of instructions that will be executed by your fuzzer. And also within this macro, you can see there is a callback function, and within that function, we initialize a client. In this case, we are using the program test crate from Solana Labs. And we initialize that client, and we load also the entry point of your program that will be invoked. And finally, we run the fuzzer on the generated data that are these fuzz instructions. The next file that we will look at is the fuzzinstructions.rs file. And this file is probably the one that you will use and edit the most. And as you can see, it contains an enumeration of fuzz instructions. And the variants of this enumeration are the instructions of your program. So it contains all the instructions of your program, and each variant also has its associated struct that it contains or holds. So we have here, for example, the initialize struct. All the structs have the same structure, so it always contains accounts and data fields. And yeah, all of that is automatically generated. So you can see that, for example, the initialize accounts struct contains all the accounts that the initialize instruction expects. So we can quickly verify. If we will go to initialize instruction, we have here author, escrow, and system program. So this is exactly what we have here: author, escrow, and system program. And also in the same way, we have the initialize data structure here. And this structure contains the instruction data that are passed and expected by the instruction. So again, if we will go to the initialize instruction, here we have receiver and amount. One thing that is different, that here the receiver, it is a public key that is expected by the instruction. However, here in our initialized data structure, there is a type that is called account ID. And if you hover it, it's basically an alias for unsigned 8-bit integer. And yeah, we use it here because the fuzzer actually generates only a random number from 0 to 255. That of course can be also further restricted, and the range can be reduced if you wish. But yeah, the fuzzer only generates an index of an account that should be reused. So we are then creating new accounts in a database that are indexed with this account, and we do not create all the time a new random accounts. So this is a way how you can reuse accounts and not to generate all the time new public key. And yeah, of course, we have the same structures also for the withdraw instruction. And what is a little bit different here is that the withdraw data struct is empty because in this case the withdraw instruction has no parameters, so that's why it's empty. If you recall, during the introduction, I was showing you the fastest life cycle. So you can see the same diagram also in our documentation in the section fastest life cycle. And if you scroll here, then you can see it. So yeah, what we have done so far is that we already, or the fuzzer for us generated here the array of instructions, and now the fuzzer will basically run and invoke all the instructions. But what we need to do right now in our fuzzinstructions.rs source file is to implement the mandatory methods that are required for each instruction. And this is the get accounts method and the get data method, as you can see here. So if we will go back to the code, it's also already pre-generated in the fuzz instructions file. So you can see that it is a trait called IXOPS, which stands for instructions operations. And so we have to implement it first for the initialize instructions, and we have two methods get data that will basically calculate and provide the instruction data, and then the get accounts method that will calculate the methods that should be passed to the init or initialize instruction. And then we have also exactly the same for the withdraw instruction. And finally, the last part of this file is the Fuzz accounts structure. And this structure serves actually as a storage or a database of accounts, and it helps the fuzzer to reuse already created accounts and yeah, not to generate all the time only random accounts, and also keep track of the, let's say, type of the account that you would like to submit to your instruction. And finally, the last file that we will look at or that has been generated is the account snapshots file. And usually this is the file that you will edit only in the case when you have some other dependencies of your program. And basically this file is automatically generated, and it helps the fuzzer to create the instruction account snapshots. It basically deserializes the accounts to the given structures that are generated here into the snapshots. And what I can recommend you also is to check our documentation. If you will go to the how to write fastest section and the first steps, here it is described that if you have any dependencies, then where you have to edit, you have to edit the cargo toml file, and also you have to add the necessary use statements in the account snapshots file. But we are not going to do it for now because we don't have any dependencies. So we can go directly to the next step, and this is to specify accounts to reuse. And here you can read some information how to do that, but we will go directly into our source code. And as I told you before, the structure Fuzz accounts contains all the accounts that are used within your program. And now what we have to do, we have to determine what kind of accounts or what types we would like to store. So if we will open, for example, the initialize instruction, we can see that here the author, it is just a signer. So we will need, let's say, a key pair to store a key pair. Now the escrow, it is a data account with a given data type, escrow, and it is a PDA account. And then we have the system program, which, and in this case, it can be only one account with the defined address of the system program. So if we will go back to the Fuzz instructions, we said that the author is a signer, so we will need a key pair here. So let's define the storage as key pair. Then here the escrow, it is a PDA account, so let's define it as, or specify it as PDA store. The receiver is in the withdraw instruction, so we will look at it later on. And the last account here is the system program. So in the case of system program, we have seen that the program accepts only one specific account. So it doesn't really make sense at this point to supply any other account to our program. We can also verify it in the withdraw instruction if it is the case. And yes, so our program all the time expects only the system program with the given address. And also we have here the receiver, which is also signer, some key pair. So if we will go back, we can basically just delete the system program because we don't need to store different variants. And then we have the receiver, and it is used as a signer, so we will need a key pair. And that's it. This is how we added the Fuzz accounts. Now it only says that the fields are not used, but we will correct it in a few moments. And the next thing that we have to implement in order to make our Fuzz test compile is to implement the mandatory methods. So first we will implement the getData method of the initialize instruction and also the withdraw instruction. So starting with the initialize instruction here, you can see that our instruction requires two parameters. So first is the receiver, and then there is the amount. Receiver is of type pub-key. So during the initialization, we have to pass a public key of a receiver. And as you already know, all the accounts that we create are stored in the Fuzz account structure, which we have here also available in this method. So in order to create the receiver account, we will just type receiver is equal to Fuzz accounts dot, and now receiver, and then we have here a helper method that is called get or create account. And the parameters here are first is it the account ID. So what we want to pass here is a random ID that we would like to choose. So that way it will create or choose already created account. And yeah, in order to get this random number, we can just use the data generated by our fuzzer for this particular instruction. So we will type self accounts, data, and now receiver. So if you recall, this was the randomly generated account ID by the fuzzer. And then we have to use the client, also pass the client, so we can create a new account. And finally, we can also pass here how many lamp boards should be airdropped to the new account if it has not been created yet. So for now, let's, for example, airdrop 10 souls. Right, so now we have the receiver key pair, and our instruction requires only the pub key, so we will pass here receiver pub key. And then there is the other parameter, which is amount. And here, in this case, we can, again, you type self, data, and amount. Right, that's it for this instruction. And then we have also the withdraw instruction and the get data method here. As you can see, this instruction does not expect any parameters, so that's why this structure is empty, and we don't have to do anything in this case. And finally, let's implement the get accounts methods. So in the case of initialize instruction, the instruction expects 3 accounts: author, escrow, and system program. So yeah, as you know, the author is the signer, and we can use the same approach as we used in the getData method. We will just create the author. So let's let author is equal to fuzz accounts dot author, and now dot get or create account, and again self, and now we will use self accounts author, like that, client, and then we can again, for example, airdrop 10 souls. Right, and in this case, the author is also signer. So yeah, we can just write here author like so, and yeah, we will have to clone it, because then we also want to pass the public key here as the account. All right. And then the next account is the escrow account, which is a PDA. So we can quickly check how the PDA should be calculated. If we will go to the initialize instruction, you can see here that it is that the seeds are the author key, receiver key, and escrow seed. So yeah, we will do it in the same way. Let's type let escrow, and now again the Fuzz accounts. Let's choose escrow. Now get or create account. And yeah, now we already defined that escrow should be a PDA, and therefore the specific implementation of the get or create account method is used. And you can see that the method now requires also the seeds and program ID parameters. And yeah, so in that case, we will again use the ID that is randomly generated. So let's use accounts and escrow. And now the seeds, I have prepared it already beforehand, so I will just copy that. Like so. So the seeds are, as we said before, author, receiver, and escrow seed. So escrow seed, we can just import it from our program, this constant. And then we have the receiver. This is something that we have to create. And we have also the program ID. So in this case, it is the ID of our program. So we can just use this one. This is the name of our program and the ID. And yeah, so the last thing is to create the receiver. And we can do it exactly in the same way as we did it in the get data method. So let's just copy that and paste it here. Like so. So here we will paste there escrow. And yeah, we actually need to unwrap it, because it is wrapped in an option, because yeah, if you, for example, specify some incorrect or invalid seeds, then yeah, the calculation of the PDA account might fail and return none. All right. Like so. And finally, the last account is the system program ID. And we said that we don't have to use different accounts. So we can simply paste here the system program ID. And that's all for the initialize instruction. And now we can implement also the get accounts method for the withdraw instruction. Again, we have here 3 accounts, which are basically the same. So we have here the system program. We can just put there system program, and then we have receiver and escrow. So we can just copy that from the initialize instruction, like so. And now let's check. Oh yeah, okay. And in that case, we do not pass receiver as instruction data, but we can retrieve the randomly generated ID from the accounts structure. So it's like so. And Now, in order to calculate the escrow's PDA address, we also need the author pub key. So we can also copy that from the previous get accounts, like so. And we do not pass any author, so in that case we can take another arbitrary ID. So let's reuse, for example, the receiver. Right, and finally we just have to finish the signer, so which in this case is the receiver, and then the pass the accounts. All right, and we are done. So for now, we didn't implement any invariance checks yet, but we would like to verify that our fuzz compiles and that it runs correctly. And for that, we can go to the Trident.toml configuration files, and we can just set up a limit of the iterations. So let's run, for example, 1000 iterations. What I usually do is also I set up the number of threads that will be executed. So for debugging and let's say writing the tests, I use only one thread because then the outputs are not mixed together and it's easier to read the logs. And also I activate the logs by switching the keep output and the verbose options to true. So let's save that. And now if we go to the terminal, we can simply run Trident fuzz run and run the fuzz test 0 and enter. And so now it will have to compile everything again because it has to compile it with instrumentation. So yeah, it will take some time. All right, so the fastest are finished. I have finally set the limit only to 100 iterations. So the fastest stopped after 101 iterations, and you can see the logs here in the console. There are different errors right now. So for example, here is some error that there was insufficient lamp boards on the account. So this is possible because the amount parameter is generated automatically, so it can be an arbitrary number, and we are airdropping only 10 souls on the account right now. But there are also other errors. For example, here you can see that there's an anchor error that says that is caused by the account escrow because the account is not initialized yet. And it's caused, or it happened in the withdraw instruction. And we know that we have two instructions. Let's check it in the code. We have the initialize instruction where we create the escrow account, and then we have the withdraw instruction where we use this escrow account. So it means that if we call only the withdraw instruction, for example, then there is no way how this escrow account could be created. So that's why we can now tweak our fuzz test. And again, I advise you to go to the documentation in the section customize instructions generation, where you have already a snippet of code that we can copy, and we will paste it in our test fuzz.rs file. And we can just replace it like this. And what it means is that we have to import also here the initialize instruction, like so. And what it means that we are here implementing our own implementation of the pre-instructions method of the Fuzz data builder trait. There are also other methods that you can implement. So if you just implement the default members, there is also the instructions method and the post instructions method. But for now, we only will implement the pre-instructions method. That basically now says that when we generate the instruction sequence by the fuzzer, there should be at the beginning all the time the initialize instruction. So that way we will all the time initialize some escrow account. There is also another thing that we can tweak in our fastest in order to make it run faster and find a crash faster. If we will go to the fast instructions, you can see that we have the accounts IDs that are now unbounded. So the fuzzer will generate basically and provide a random account that is one of the 256 random accounts that could be generated. But it is most probably not necessary, for sure not in our use case. So we can here restrict the number of generated accounts. And again, let's go to the documentation. And here is a section that is called how to use arbitrary crate. Here you have some introduction, but you can here copy this macro and paste it here. Let's just format it a little bit. And what it does here is that this macro will basically override a default implementation for this data type, and we can here now specify our custom range. So let's say that, for example, we would like to generate here a random value from 1 to 3, and therefore we will have only 3 accounts for the author. And let's do that also for the other accounts. Step system program is not important for us. Then we have also the receiver account, and then let's do the same also for the accounts that we submit for the withdraw accounts. So that way we will greatly reduce the number of accounts that will be generated and reused. And the last thing that we will implement in our fast test will be the invariance check. So let's go to the implementation of the instructions operations trait of the withdraw instruction. And here we can just implement other missing optional default members. And as you can see, we have here the check method. There is also another transaction error handler method that we will not need today, so let's delete it. And yeah, so now we can implement our invariant check in this method. And what we would like to do is that we will check it in the withdraw instruction. So we have here the escrow account, and actually when we close the escrow account, everything is transferred to the receiver. And obviously here we expect that the receiver should be the same as it is saved in the escrow account. If it is not the case, then some unauthorized user would be able to withdraw this escrow account. So this is what we would like to prevent, and that is what we will check, that it will not happen. So we will write if let some escrow pre. We will check if there is some account, some escrow account in the pre-instructions snapshot. So the pre-instructions, this is a snapshot of account before the instruction was invoked. And the account is here as option because it can be closed. So if you would do the same for the post instructions, then you would have no account there and the option would be none. So we have to just check if there is some escrow account, and then we would like to verify that if the receiver key, so this is the signer, is not equal to the escrow accounts receiver. If pre-instruction receiver key is not equal to escrow account receiver, and if it is not the case, it is possible, but in that case we expect that the receiver's balance shouldn't increase after the withdraw instruction is invoked. So we will add another condition. If pre-instruction receiver lamp ports are less than post instruction receiver lamp port, then we would like to return an error. So let's return, for example, balance mismatch. All right, we don't need the instructions data here, they are known. And yeah, so now it says that we could just express it with one X statement. That's why it's yellow, but anyway, it's not important right now. And that's it. That's all our check. So now let's try to run our fuzz test if we will find a bug in our program. And in order to run our fuzz tests faster, let's go to the Trident toml config, and yeah, let's clear the iterations limit. Let's set it to 0. Also the threads, so it will use the maximal or the default number of threads, which is number of CPUs divided by 2. We don't need the we don't need the output right now, so let's set it to false. But what we can do is that we can stop the fuzzing if there is a crash found. So we can set the exit up and crash to true, save, and yeah, let's start the fuzzing again. All right, and now the fuzzing is done and it stopped because it found one crash after approximately 50 seconds. And it also saved all the relevant data to this crash file that we will be able to use to analyze our crash. So let's copy this path. And now in order to run this particular test in a debugger, we can just type Trident fuzz run debug, and we would like to debug the fastest 0 like that. And now we just want to specify the crash file that we would like to use in order to load the inputs. So let's run that, and now again it needs to compile because yeah, the program has to be compiled with a debug profile. So let's wait a bit. All right, so now we are in the debugger. As you can see, we have here backtrace of the program before the crash. And if you scroll up a little bit, we have here also a log message that says crash detected, custom check after the withdraw instruction did not pass. And we have here also the error that we return from our check method, which is the balance mismatch. So it detected the crash, and it didn't pass our invariant check. And now if you would like to debug what happened and what were the inputs, so you can scroll up again, and here you can see that here is the sequence of instructions that has been generated for the particular fuzz test. So first of all, we have the initialize instruction, so it will be always there because we have defined in the pre-instructions that we would like to start with the initialize instruction. And we have also the indexes of the accounts that were chosen, which are 2 for author and 1 for escrow. The system program, it is some random number, but we don't really use it in our fuzz test, so we can ignore it. And then we specify that the receiver should be the account with index 2, and we will pass also the amount of 8,109 lamp boards to be transferred to the escrow account. And then we have 2 withdraw instructions that use different accounts, different combinations. So now if we will scroll a little bit down, we can see the actual sequence that has been invoked. So first of all, we have invoked, or the fuzzer invoked the initialize instruction, and then it invoked the withdraw instruction, the first of the 2, and then it crashed. So as you can see, we are using the receiver 1, which is actually a different receiver here than what we have initialized. And we use the same escrow as during the initialization. So the escrow and the receiver shouldn't match, and the crash has been detected. So that's it for today. We were able to successfully implement a simple fuzz test using Trident and discover a vulnerability in our program. I hope that you will be able to use Trident also in your projects. And you can connect with us via Discord, and also feel free to contribute on GitHub. And yeah, we are planning additional features to make it more user-friendly and also faster. So stay tuned. Thank you for today, and see you next time.